Hey everyone, Morgan here. So we're going to be talking for the next 4 or 5 pages about a relatively complex idea called hybridization. And it's very visual. So I'm going to be using some models and drawing some pretty bad pictures, but I think you should all just pause the video for a second and go find yourself a set of colored pencils or some crayons or markers or something, because it will definitely be helpful with what you want to do, okay? All right, so the idea called hybridization here, okay, it has a lot of different stuff going on with it. And there are reasons that we have to talk about this that deal with the structure. Now, this is a model of methane, okay? And this is going to be our theme for starting out with. This is your classic tetrahedral arrangement of atoms. Okay? So why do we have to talk about this? Well, it turns out CH4 might be tetrahedral, but there are no tetrahedral shaped atomic orbitals. So, what are the 4 equivalent orbitals that we are actually using to form the bonding in a CH4 molecule? Now, hopefully you remember the s orbitals. 1s, 2s, 3s, they're spherical, and the 2s is bigger than the 1s, and the 3s is bigger than the 2s, okay? We have p orbitals that take this geometric arrangement. We even have d orbitals that take these arrangements. Now, none of these are tetrahedral. And we know that when we're doing something like this, okay, the s orbital is where the electrons are going to go first. That's the Aufbau principle. So that's just not going to work for us anymore. So what we're going to do is we're going to form new orbitals. And these orbitals are called hybridized orbitals. And they only form when a molecule is forming. So they're not just on a lone free atom. Now, when we're talking about CH4, we're going to need 4 equivalent orbitals to do this. So I'm going to take my carbon, put it right here. Do that in black. Try to color code things today. Now, I'm going to have 1 orbital that goes up like that. One that's there. One that's here. And one that's there. Now, by my art skills, that's actually better than normal. my drawings are usually really, really bad. But there are really good representations of this in your textbook. Now, this would have about 25% S character and 75% P character. Now, we should go into a little bit more detail about what's happening here. 4 things are attached. So if 4 things are going to be attached, I'm going to need 4 hybridized orbitals. And the electrons go into the s first, so the hybridized orbitals will always start out with an s every time. And then I'll use 3 p's. 1 plus 3 makes 4. That's how many things are attached here. And that's how we came up with this sp3 hybridized orbitals. Now, in this model, if you're looking at my gray clouds here, with, picture them without the white ones on the end, those are those hybridized orbitals. That is what they look like. Okay? So pause if you have to finish this diagram. Okay? I'm going to get ready here to move on to my next page. And we're going to look at a few of the other possible hybridizations. Okay? All right, so sp2. sp2 happens when we're trying to work with this, okay? Now, we have 3 equivalent bonding sites, and they all happen to be planar. This is flat, okay? So what I'm going to do, I'm going to start off with a little dot here that's going to represent my atom, okay? Now, I am going to draw 3 equivalent orbitals there, there, and there. Those are the sp2 hybridized, okay? In red, sp2 hybridized. However, I've only used 2 orbitals so far out of the p. I've used 1 of the s, and I've used 2 from the p. That means I have a p that's left over. And I'm going to draw that in the green. So this is going to be an unhybridized. Hybridized. Unhybridized p orbital. Okay? So in this model, it would be sticking out this way and out that way. Now, I can kind of show that to you with this model right here. The 3 equatorial sites are my 120-degree angles, okay? And then these without the other atoms on them are going to represent the unhybridized orbitals, okay? Now, wouldn't hurt if we actually knew that that angle was 120 degrees. Okay? Now, what about if we're doing something that only has 2 atoms attached to the central atom? That's going to be right here. That's linear. Okay? Now, I still have to hybridize because I don't have 2 identical orbitals to start out with. So here's my little dot, which would represent the atom itself. Now, I'm going to have here an orbital that comes out like that, an orbital that goes out like that, and those are the sp hybridized. Now, I have not used 2 of the p's. I have an s and I have a p. So this is kind of 50% s character and 50% p character. It's really a bit more chubby than that because of the s character, which is quite spherical. Okay? So I've got a p orbital that I have not used yet. I'm going to try to keep the colors consistent. So up here I had this unhybridized p orbital, and let's call this one a z. Okay, that's the one in the z orientation. So here, unhybridized p sub z orbital. Except there's still another one to go. Okay, so that one would actually go off in this direction like that. And that is an unhybridized py orbital. Okay, now when looking at those, this is one orientation, that's another orientation, and yet here is my third orientation, which is the S and the P, and that used the P from the X direction to do that. Okay? The angle on the pink ones here would be 180 degrees. And once again, this is what it is that we're looking at right here. Okay? Now, what if I have 5 things attached? That is going to require 5 orbitals, and we will call that a dsp3. All right? So first off, that little black dot there is the central atom. Now, I have a lobe coming up and one coming down. I'll have one coming out in that direction, one going out in that direction, and one going out in that direction. Now, what I can kind of picture this as is a combination of 2 of the things that we have already looked at today. I've got this one, and I've got this one, and I go 1, 2, 3, boing, and I end up with this one. Okay? These up and downs here are the ones that have the darker green in the model. And the ones going around the middle are the ones here with the lighter green in the model. So, this angle is 120 degrees, whereas that angle is 180 degrees. And I would see this in something like a PCl5 molecule. Now, D2sp3. There's my central atom there. Okay. I'm going to have an orbital that is in the z direction. I'm going to have an orbital that is in the y direction, and I'm going to have an orbital that's in the x direction, and it really doesn't matter which one we distinguish as x, y, and z, okay? But I can kind of see that right here with this model. Now, I did the 3 equatorial ones in light green, and I did the 2 axial ones in the dark green. So the angle between the 2 axial ones, okay, which is from there all the way out to there, is 180 degrees. But all these other angles are basically 90 degrees in every other possible orientation that I might come up with here. Okay? All right. Take a second, finish your drawings, pause as necessary. Okay? And what we're going to be doing now is actually moving on to page number 9. Okay? Bounce some models around here. Go to the next page, number 9. So, I have a pretty convenient little table here that I can look at and fill in, okay, that helps me to keep track of what's going on here. I'm going to number this 2, 3, 4, 5, 6, and 7. So the number of things attached to my central atom. And again, as an example, linear, that would have 2 things attached to my central atom. The white one on the left, the white one on the right. So the hybrid orbital number for that's a 2. In fact, the numbers here are the same. It's the number of hybrid orbital numbers attached. If you only have 2, the geometry around the central atom is linear. It is trigonal. Then if we get up to 4, it's tetrahedral. Okay, 5, triangular bipyramidal, octahedral, if it's 6 things, all right, and pentagonal bipyramidal when 7 things are attached. And that's pretty rare. Now the hybridization when 2 things are attached will be SP, those are lowercase letters, SP2, SP3. Now, I say DSP3. You can also say SP3D. The difference between them at this level, there isn't. In like an advanced inorganic chemistry class, you'd see some differences. D2, SP3, D3, SP3. It's very rare, but it does actually exist. It can happen. Okay? So, I want to look at some specific molecules for the next couple pages and actually draw detailed pictures of the bonding that exists in them. Okay, so we can talk about it. Methane. We have a carbon in the middle. Now that carbon is attached to 4 things. So those 4 things are going to be represented by sp3 hybridized orbitals. So blue is what I was using if I'm remembering correctly. There are my 3 sp3 hybridized orbitals. Okay? Now, it turns out the hydrogens are only bonded to one thing. They don't have to hybridize. They can actually just use their 1s orbital because you're only attached to one thing. Okay? And we know from our diagram on page 7, okay, page 7, maybe page 6, page 7, I'm pretty sure, that s orbitals, okay, they are spherical, just perfectly spherical. Now, what is it that I am seeing here on the page? This bond is made up from the overlap of an sp2 and a 1s orbital. Now, it has s character because there's s involved. So it is called a sigma bond. That is the Greek letter sigma, S-I-G-M-A. And we say it is a sigma 1s sp3 bond. We could just as easily say sigma sp3 to 1s. That works too. And in fact, this is the same, this is the same, this is the same. I have 4 identical bonds. They are all sigma bonds. 1s sp3. So from this point forward, I want you to think of sigma as single bonds or bonds with any s character. Okay. Now, for our next one, we're actually going to be looking at something that contains a double bond. So, let me draw my, just this real fast structure. That's what this looks like. So, a carbon and a carbon. Now, this carbon is attached to 3 things. That means, am I in red for this one? Let me double check. Yeah, this is a red. I remembered. This means I'm going to have sp2 hybridized orbitals on the carbon. All right? Now, each of those hydrogens, which I'll put out here, does not need to hybridize. All right? And that gives me overlap here, which I can describe as a sigma bond, which is sp2 to 1s, or I could just as easily say 1s to sp2. They both work. Now, hold on. Hold the phone here. There is a p orbital on the carbon that I did not use yet. And I'm going to draw that in here, and I'm going to draw that in here. And if I got that right, I'm color coding the same way I did on the previous page. Now, this is actually going to represent the second bond of the double bond. The electron density I cannot accurately tell you whether it's above or below. It's in both places, Heisenberg uncertainty principle. So this is not triple bond, this is a double bond, okay? The first bond, okay, that first bond there, number 1, was a sigma sp2 to sp2 bond. Now, the second bond in it is a pi bond. And we'll say that that's pi in the z direction. Whichever of the 3 directions you choose is great. That doesn't really matter. Okay? So that's what the bonding would look like in C2H4. Okay? A sigma sp2 sp2, a pi z, and then 4 sigma sp2 to 1s bonds. Okay. Now, as we move on to page number 10 here, it's going to be a little more complicated than that, but I think it's something you can follow along. I should point out that all these pages right here, 7, 8, 9, and 10, they're background material. They're support material. They're not actually going to be tested on the AP exam. Okay. Now, C2H2 is a carbon triple bonded to another carbon. Okay? So, to put that together, all right, I need to first join together my 2 carbon atoms in the first bond that comes between them. So I'm going to put a dot here and a dot here. That's just, well, let's do it. It's the carbon and it's the carbon. Let's draw those 2 carbons. Okay, now the sp is attached to 2 things, so it's sp hybridized. The sp, I think I've been doing in pink. There we go. Now, out here I got a hydrogen with a 1s and a hydrogen, the 1s. So this bond right there is a carbon sp, I'm sorry, it is a sigma bond, sp to 1s. Trying to use the same notation straight through. Now, on the carbon itself, there are still 2 p orbitals that have not been used. One in the z direction, and then I'm also going to do one that is in the y direction. I cannot put them both in the same orientation, because if I did, the electrons would repel each other. So, in here in purple, I have a pi y. In green, I have a pi z. And in the middle, in pink, I have a sigma sp to sp. All right, there you go. CO2. All right, carbon. Double bond to oxygen on both sides. But don't forget the oxygens have lone pairs, and those lone pairs need a place to live. Okay, that's important. So I'll draw my carbon, and what I'm going to do is put an sp on both sides, because the carbon is attached to only one thing. Okay? Now, the oxygens. All right? The oxygens, I'm going to draw out here in red, O and O. Now, they're attached to the carbon, but they also each have two lone pairs. Lone pair, lone pair. Oxygen. Attach it to the carbon. Lone pair, lone pair. That's sp2 hybridized. So that's about the equivalent of me laying this, okay, right over to hook up with this. That's what's happening there. Okay? Now, important to note, the carbon still has two p orbitals that were not used. So I'm going to do one, the pz, which I've been doing in green, like that. Now each oxygen, I've used two of the p's because they were sp2. Maybe I should actually label that for you. sp2, sp, sp2. So now, I still have one left over on the oxygen. Over here, I'm going to say it's the one in the Z orientation. And I'm going to get this nice overlap like this, both above and below the axis. And that's going to make a pi, and we'll call it a Z. Now, what about in the other direction? Well, it turns out this carbon also has a py orbital that is unhybridized. This has one p orbital that's unhybridized, so I'll make it the one in the y also. And draw that like that. Okay? So what I have here is a pi y. Now, I'm going to go grab a model. Hold on one second here. This is going to help a lot. This is a model of CO2. And what you're noticing is that the double bond can't be in the same orientation both ways. Doesn't work that way. So actually kind of picture this as the first bond being invisible between the two atoms, and these two gray pegs here as being the second bond, which occurs both above and below the axis between them. Okay? And this shows you why I have to have the one that's in the purple orientation, and I have to have the one that's in the green orientation, because they both can't be at the same place at the same time. Doesn't work that way. Okay, cool. PCl5. I have a phosphorus in the middle, and it has 5 things attached to it. So I'm giving it an sp3d. Okay? Now, I also have the chlorines, and each chlorine has 3 lone pairs. So, Cl, 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 Cl. So the chlorines are attached to 4 things. 1 phosphorus atom and 3 lone pairs. So in each case, that means sp3 hybridization. Now you know why I didn't go to art school. I would have told you I got kicked out of art school, but I would have never gotten in. And then each of these has a lone pair in them. Lone pairs cannot be homeless. They have to have an orbital to reside in, and that's going to be a hybridized orbital. Okay. Now, nitrogen, N2, is a good example of what's going on here also. So I've got my nitrogen. There's a lone pair on either side. So here are my sp, because it's attached to two things, lone pair and nitrogen, lone pair and nitrogen. Now, two unused orbitals, unhybridized. The p orbital in the z direction and the p orbital in the y direction. So what I'll do is I'll call this bond a pi y. The green I'll call a pi z. And the one in pink is a sigma sp to sp. And then up here, these were all sigma sp3d to sp3s. Okay, that's the whole idea behind hybridized orbitals. Okay, please remember that the sigma bond is the first bond, and if there is a second bond, like with a double bond, you have a sigma and a pi, and if you have a triple bond, you have a sigma and you have two pi bonds. Okay, folks, thanks for tuning in. This is Morgan, signing off.